Tigadan 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 pam pam tigadan 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 pam pam tigadan 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 pam pam tigadan.
Our final presentation today comes from DK Panda, professor and distinguished scholar at The Ohio State University. DK, how are you this morning?
Pretty
this
good.
Afternoon, I would say.
Yeah, good morning. Good morning to US people. Good afternoon. So again, Hussein, Brian, Sydney, all of you, it is very nice seeing all of you virtually. So I hope things will be better next year. We'll see. So today I'll be just like all the earlier years. I'll be very happy to share some of the things what we have been doing recently and what are the latest trends. So the topic will be like the designing the high performance and scalable middleware for HPC, AI, and data science. So as most of you know, just like Addison said, we are in a very exciting phase. We are trying to go through the number one system is in Japan, but as Addison said, I mean, so hopefully this year we'll at least see either some of the machines from China being declared as exascale systems, or we'll see some systems in Europe. Okay, so just give me 1 minute. I'm trying to clean up the screen here. Just give me 1 minute. Okay, so in this context, as many of you know, even Addison's talk indicated, I mean, so we are in a very exciting phase, combining HPC, deep learning, machine learning, and also the data science. So we are trying to run all these kind of applications on the common system. So the question is, can we actually have a convergent software stack? And in this case, we are trying to have an MPI-driven software stack be used so that it can actually help us in designing and getting the best performance from all these systems. And of course, we want to do it on the on-premise system. We also want to do it on the cloud. So in this context, we have been working, as some of you know, in all these different domains. I'll try to summarize a little bit from the very beginning, from our MVAPIS project on the MPI side, what kind of the latest results we have. And then I'll move into the high performance deep learning, machine learning, and the big data with the Dask. And then gradually, we're also moving our software stacks to the cloud. As Addison said, around 7% kind of thing. People are now using cloud. So we are trying to push our software stacks there. And then I'll talk a little bit about some of the commercial support and value-added products through a commercial spin-off called xScale Solutions, which is also a sponsor of this event. And then I'll conclude. So this is an overview of the MVAPIS2 project. I am assuming all of you are familiar with this. If not, just to give a quick intro, we started this project almost 21 years back on the day one of InfiniBand. Prior to that, we are working on Myrinet, Quadrix. And when InfiniBand was there on the October 2000, we were the very first group in the world to jump in and have a high performance MPI on InfiniBand. We had our first demonstration at Supercomputing O2. And since then, we have been continuously enhancing it with respect to MPI standard, with respect to all the different networks like Omnipath, IOR, Ethernet, Rocky, AWS EFA. And just last week, we made the new release. Now we have support for the RockPort networks and also Cray Slingshot. And the Cray Slingshot 10 is currently supported. I'll show you some numbers. And then in the next few months, we'll have the support for Slingshot 11. And of course, we have been continuously moving for all the different kind of the CPUs, GPUs, and also the very latest GPU. So I'm very proud of my team who have been working hard all over the 21 years. Now this stack is being used by more than 3,200 organizations. And just from the OSU side, we are hitting very close to 1.6 million downloads, just from the OSU side. Of course, the stacks are available through Red Hat, SUSE, OpenHPC, SPAC. We don't keep track of those. But in addition to the downloads, we have been enabling, as many of you know, for the last 15, 16 years, we have been enabling a lot of top 500 systems all over the world. So this is the broad overview of our architecture. We have a view of the convergent view, like HPC, DL, ML, data science, everything looking together. And here is the support for all the different networking technologies and their features. And then we have, these are all the CPUs, GPUs, and DPU. And then this is our internal architecture where we actually have the runtime, trying to take care of the best, let's say, point-to-point, collectives, startup, energy awareness, all those issues. And then we link it through the upper level parallel programming layers through MPI and PGAS, hybrid MPI PGAS, for not only for HPC, but also for machine learning, deep learning, and data science. I'll show some of those examples soon. So we have multiple versions based on like the demand in the community and all. We have the base version, MHAPIS2, then we have an advanced version, MHAPIS2X, and especially this version, MHAPIS2 GDR, which is very much highly optimized for GPU clusters. Okay, so I'll try to show some of the designs and the very latest performance numbers on these machines. So this is the latest, as Addison said, like the AMD systems are getting a lot of popularity. So here it is like the AMD Milan plus InfiniBand SDR200. So this is the MHAPIS2 236, the previous release. As you can see, within intra-node, 2 cores within the same socket, we are actually able to deliver MPI level latency of like 190 nanoseconds, 190. And then internode, we are around 1.9 microsecond. And as you can see here, we are able to get very high bandwidth intranode as well as internode, like the SDR200. So that is the point-to-point, but as many of you know, the collectives play a very significant role in not only in terms of HPC application, but now also all the MLDL applications. So we have been heavily focusing a lot of optimizations on the collective. So here, these are some of the numbers I'm sharing where we have done a very tight integration with the SARP. That is the Mellanox NVIDIA SARP, as you know, they support in-network computing. But SARP has some kind of limitations on some number of PPNs, some kind of communicator you can use. So we have done a very tight integration with our stack. And these are the numbers taken from TAC Frontera, which is one of the largest InfiniBand systems. As you can see here, I'm showing numbers of almost 8,000 nodes. And as you can see that, of course, the MHAPIS2X has a lot of software-based solutions, but with SARP tight integration, as you can see, like MPI barrier, these are all blocking collectives. We can reduce performance by a factor of 9, all reduced by a factor of 5, and similarly reduced by a factor of 6. So these are the blocking collectives. And in many of the slides, you will see the references to some of our publications. So if you are interested in knowing more, you can always go and read some of these papers. But in addition to the blocking collectives, there is a lot of focus recently on the non-blocking collectives. And if some of you know, like a blocking collectives, let's say I do an all-to-all, unless the all-to-all finishes, I am not able to go to the computation. So that doesn't give very good performance because there is no overlap of computation with communication and it doesn't scale. So this is where MPI-3 standard introduced non-blocking collective. So that means I can initiate the non-blocking collective, but while it is going on in the background, I can actually do some computation. So it actually provides good overlap of computation and communication, and then I can get very good performance. So gradually, some of the codes, people have started now moving from blocking collectives to non-blocking collectives because you need to redesign those codes. But at the same time, a lot of middlewares didn't have those kind of very good support for non-blocking collectives. So it is a chicken and eggs kind of thing. So we are focusing a lot now providing those kind of support for non-blocking collectives purely on the host. And next few slides, I'll also try to show on the DPUs. Okay. And then after you redesign your application, you will be able to really put them together and get very good performance. So this is like a non-blocking collective. We are trying to take advantage of the SARP. This is already available in the MHAPIS2 237. This is purely host. Okay. In the host itself also, as you can see, like let's say the blue line is the earlier MHAPIS2 236. This is the green line is our 237. As you can see here, I barrier, we are reducing just even at 32 nodes, we are able to reduce by a factor of 4.4. But at the same time, see the overlap. Overlap, we are able to improve significantly, like this is the right-hand side. So as you can see, we are able to go to 60 to 50% overlap. So same thing for I/all reduce. As you can see between blue and green, we are trying to reduce the latency and also increasing the overlap. So that means if the applications can be redesigned, even on the host-based system, you should be able to, your overall application performance will improve. Same thing here is also I reduce. So here what is happening, overlap was there in the earlier design. We are not able to improve that much, but we are able to improve the latency. Okay, so that means this is additional benefit. You can still exploit the overlap, but your overall latency will be lower. And same thing also, you see the IB cast. Actually, there was not much overlap, and we were able to. We are able to reduce the latency, and then the overlap was not there, and we are able to push it. So these are again on the purely host. Okay, I'll come to the DPU in the next few slides. So then, as I indicated, we have been like, there are two newer networks in the market these days. One is the RockPort networks. If some of you are not familiar, it's from a Canadian company. We have been working with them closely. So the latest release 237 has actually now official support for the RockPort network. So here it is trying to show some like a small message, medium message, latency, and bandwidth. So we get around like a 3 microsecond latency internode. And bandwidth wise, we are able to get like a 10 to 9 megabytes per second, and then the 20,000 megabytes per second in the bidirectional bandwidth. And this is the most important. This is the Cray Slingshot architecture. So we have that support already. This is for Slingshot 10, and they actually operate in a rocky mode. The Slingshot 11 has not come yet, or it is still there. We don't have any access yet, but once it is available, we'll be able to do more evaluation and support in the MHP2 library. So here we are trying to show some comparison with our MHP2 stack with OpenMPI and the Cray MPitch, which is the native MPI on the system. So here you can see intra-node. This is like the AMD EPYC ROM CPUs. I'll have the GPUs numbers later on. So here, as you can see, even within the intra-socket, we are able to like a 220 nanoseconds. We are able to provide the latency and bandwidth. As you can see, this the teal color. We are able to deliver very good bandwidth. Even internode, it's around 2.55 microsecond, and bandwidth is very similar across all the stacks. But if you take a look at the right-hand side, these are some of the collectives, and we only have like a small scale runs here. That is the only access we could get. As you can see in the collectives, we are able to significantly do better than OpenMPI and also the Cray's MPI. So continuously we'll be improving on these. So, but if you have any Cray Slingshot system, you should be able to directly download our stack and then start using it even from now onwards. So here, those are some micro benchmark numbers. I just want to highlight some application-based number. This is the project we are working with the EPFL, and the system is actually at the CSES. We have been working with the EPFL neuroscience application group. So here you can see like this is the numbers taken on almost 10,000 cores, comparing with HP MPI and MHP2X. As you can see, this is for the neuroscience mini application. We are able to even deliver like almost 36% improvement with a random neighbor selection and around like a 6.5% improvement compared to consecutive allocation. So similarly, we are working with a lot of other many national labs. Here are some results from the Oak Ridge National Lab with the Summit system. This is the, we're working very closely with the HPC library group. And so here again, you can see they have done a very exhaustive evaluation. They presented a detailed talk at the MHP User Group Conference, which we do annually. So here you can see like a MHP library is able to deliver almost 10 to 20% faster compared to the other library. Similarly, here there is another example from Idaho National Lab. They are the one of the largest users of MHP2. So they have been running a lot of like a nuclear energy applications together with Moose and PETC. So we have been able to continuously optimize in those environments. So now switching the gear a little bit, as many of you know, the NVIDIA Mellanox has introduced the DPU, which is the data center processing unit. So I call it like an executive secretary model. So if you see the DPU adapter, now, of course, these are like the host, like an executives. Now, earlier InfiniBand had the RDMA engines, but now they have ARM cores, programmable ARM cores. So you can think of, we have a bunch of secretaries trying to help a bunch of executives. Okay, just like what we do it in a normal, our organization level things. So the question is how we can redesign MPI library or any other middleware, keeping this kind of newer architecture in mind. So in the beginning, we have started trying to offload some of the MPI functions, and especially here, we have focused on the non-blocking collectives, as I indicated earlier, because just like secretary, let's say you want to establish a video call, or just like for this conference, I'm sure a lot of CSCS people help to Shen to organize this. So you can offload those tasks to them and they can take care of it. And then in the end, you say, oh, the dates are finalized, timings are finalized, kind of thing. So then you can have actually overlap of computation with communication. So same model, we are trying to bring it to the DPU. So here we have actually carried out, taken some 3 major non-blocking collectives, MPI, IAll2all, IAllGather, and IBcast, and they have actually been integrated. So there is a library called MVAPIS2DPU, which is available from the Xscale solution side. So this is where the new product is coming out. And I'll show some numbers there, and a lot of people have been already testing this library on their system. So if you would like to get a copy of this, please feel free to send us an email at this address, and we'll be very happy to give you a trial license. So let's take a look at some of the numbers. So this is like the non-blocking all-to-all, as I indicated. So we want to exploit overlap. So if some of you are familiar with the MPI library, we have an eager protocol for small messages and a rendezvous protocol for large messages. And especially the small messages, you get some kind of an overlap because it is a copy-based approach, but not significantly. And rendezvous, it is very hard to get because you are trying to send an RTS, CTS. So both senders and receivers are involved. But if you offload that to the DPUs, so now the hosts are just like executive, they are initiating the all-to-all call, and then they tell the ARM cores to take care of the communication. Okay, so it's completely offloaded, and now you can see your overlap capabilities increases significantly. So this is like the red bar, as you can see, these were very tiny, but now with the MVAPIS2DPU, the green, we are able to go up to like a 90%, 100% overlap of computation with communication. So now let's see what is the impact. So here we are measuring this a part of the OISU micro benchmarks. These are the standard numbers we are presenting with the standard benchmarks. So you can also reproduce these yourselves. So if we do the compute plus communication, so that means we initiate the all-to-all and perform some computation and then measure the time. Okay. So in that case, you will see since the basic MVAPIS2 didn't have the overlap, it takes more time. Whereas the MVAPIS2DPU, since we are offloading it to the ARM cores, the CPU cycles are free. So the CPU can actually perform the computation. And here you can see this is like a 512 process experiment. This is 1,000 process experiments. We are able to get across the range almost 20%, 22% improvement. Okay, in the actual, in this case, the all-to-all micro benchmarks. So then what we did is, so these are the micro benchmark level, but how about the applications? So here we worked with San Diego Supercomputer Center. So they have a P3D FFT application. And as many of you know, a lot of applications use FFTs. So we worked with this team. So they had actually a blocking all-to-all. So we worked with them to rearrange to make them non-blocking. Okay, so of course, some code reorganization need to be done because you have to move some earlier computation following the communication. So they were able to give us a version. And now when we tested it, as you can see, this is at the application level with a different grid sizes like 1K by 1K to 2K by 2K to 4K. This is on a 256 process. This is 512 process. See the numbers. At an application level, we are able to get 20%, 18% benefit. That is on 16 nodes. On 32 nodes, similar kind of trend holds good, like a 21%, 18%, 14%. So we are still continuously trying to enhance, but as you can see, with the new DPU, hardware is the same. Now with an appropriate software, you will be able to really boost your application level performance here. So that is actually just IAll2all. Gradually, we are going into all other collectives, like IAllGather is another collective here. At a micro benchmark level, at the OMB level, that's OISU micro benchmarks, we see almost like a 41%, 48% improvement. At the non-blocking Bcast, 57%, 58%, 48% improvement. And then this is an iScatter. Even it is much more higher. This is not available in the release. It will be available in the next release. Almost 60% kind of benefits. So now the question is, can this kind of a support, as I said, it's like a chicken and egg. with this kind of enhancement to the MPI library, can now the applications be redesigned? So here again, we are always looking forward to collaboration. If any of your applications are trying to use like these non-blocking collectives, or you are willing to change those blocking collectives to non-blocking collectives, we'll be very happy to work with you to see how we can boost your applications on these kind of DPU-based systems. So now let's go back to the GPU things. I mean, GPU has been there for many years. The NVIDIA GPUs have been there. Now, of course, the AMD GPUs, Intel GPUs are coming. Now, if some of you remember, like almost 10 years back, we worked very closely with NVIDIA and then at that time Mellanox to bring the GPU Direct RDMA into the MPI integration. And that has hold good, and it has become very popular these days. A lot of other MPI libraries, collective libraries like Nickel, a lot of other middlewares are exploiting the GPU Direct RDMA. So here it is like a sample number. If you see GPU to GPU, GPU from one node to the GPU of another node, not on the same node, we are able to deliver like a latency of 1.85 microsecond. Okay, we can move data from one GPU to the other GPU. And then, of course, the bandwidth and bidirectional bandwidth, we are able to boost by a factor of 9 and 11. Now, that is like just a single GPU. But now if you see, there are a lot of dense CPU-based systems are coming. Okay, like a DGX2, a lot of other things. The GPUs are connected with NVLink. Every node you have like almost 8 GPUs, 4 GPUs kind of things. So we have been pushing a lot of optimizations to boost the performance on this kind of system, because these are the next generation systems, not only for HPC, but also for the deep learning, machine learning kind of things. So this is the very latest thing. We just had a paper accepted at the SCW workshop in the IPDPS. We'll present it in the May, but look at the number. So this is for all-to-all-V. A lot of scientific applications use actually all-to-all-V in addition to also all-to-all. And all-to-all-V is very difficult to optimize because it is a vector variant. But here what we have done, we have tried to optimize both of them. Okay, so these are some of the numbers. On one node, 8 GPUs, and here there is a 16 node in the same configuration with 128 GPUs. So what we are comparing, the T line is our design. Then we have the previous MIPS2 GDR236. We are comparing with the Nickel library. We are comparing with OpenMPI, the very latest version. As you can see, the T with the latency wise, it is able to deliver far better performance. Here, even compared to Nickel, we are able to improve by a factor of 13 for small message range, and then even for the large message range by a factor of 1.2. Now that is the micro benchmarks level, but then if you link it with the application, so this is where the HepT library I mentioned earlier. Now, if you link it with that, because the HepT library utilizes all-to-all-V, at an application level, within a single node, we are able to boost the performance by a factor of 5. Okay, but then as the system size scales, look at the 128 GPUs, we are able to boost the performance factor of 28. Okay. So these are the kind of the benefits you see if you can optimize the runtime, and this support will be available in the 237 in another 2 to 3 weeks. So if you have this kind of your applications on the GPU-based system, dense GPU-based systems, you can try to actually utilize this. Now, the other direction we have been recently exploring on-the-fly compression. Now, most of the time, the GPUs, as many of you know, they have always focused on computing. But in the past, we have actually utilized it for even some of the collectives like a reduce, some data type processing. So we are taking to the next layer. The thing is, if let's say an application utilizes large messages, can we actually compress before even sending it? Okay, so if we can do it in a lossless manner, then not only we can, of course, there will be some overhead on both sides, compression and decompression, but we want to do on the fly. But the message size will be effectively reduced. So that actually leads to lower latency and higher bandwidth. Okay, so that is a new direction we are trying to explore to utilize the GPU cores, because a lot of cores are just sitting there, and how to effectively utilize this. So this is a paper we presented last year. This got the best paper finalist award at the IPDPS. And this code, by the way, is already available in the latest MIPS2 GDR. So we worked with an AWP ODC application. Some of you might be knowing it's a seismic earthquake simulation. And on this on the fly, of course, there are all different versions. That is like a baseline. These are all the different compression schemes. And of course, our goal is to have lossless compression so that the application still should run correctly. right? And that's what we actually validated here. And now you can see that this is like a throughput. We are able to, on a 512 GPUs, we are able to push the performance by 18%, and then effectively reduce the runtime for time step by 15% to 26%. Okay. And now we are taking it even to the next step. So those are like the point-to-point message compression. But now you can think of redesigning all these collectives. Okay. So this just the paper just got accepted last week. We'll be presenting at the ISC conference in Hamburg in June. So here we have taken that again, the dense collective all-to-all, because a lot of applications spend a lot of time there. So here we have two applications. One is the traditional PSDNS, which is HPC application, and this is a deep learning application using the deep speed. Okay, that is a newer framework which is coming from Microsoft. So with this compressed version, as you can see, we are able to even for the overall latency, all-to-all latency, we are able to reduce by almost 29%, and even the deep speed, we are able to reduce by almost 36%. Okay, so this will be again available in the next release, and people should be able to take advantage of these new schemes. So those are some of the NVIDIA GPUs results. We also have supported AMD GPUs results since last AMD GPUs from the last few releases. So here we are comparing again the MFS2 GDR236, which is already available, and then the OpenMPI, the latest version. So as you can see, this is like an inter-node point-to-point latency, inter-node. Here we are able to give like a within the node, two AMD GPUs. These are MI50s. So we are able to get like a 1.75 microseconds, and across the node, it's around 4 microseconds. But then on top of the collectives, if you try to take a look, we are able to significantly provide the benefits in our collectives compared to like this, the Bcast and all reduce compared to OpenMPI here. Now going back to the Slingshot, as I said, like we support the Slingshot 10. So here again, this is not earlier I showed the host-based number. This is actually with GPUs. So these are with AMD EPYC Rome with AMD MI100 GPUs. Again, we are comparing the latest MFS2 GDR with OpenMPI and with a CRAM pitch. So as you can see, intra-node, in like GPU to GPU, we are actually performing the best. In a 2.68 microsecond, we can actually communicate between the AMD GPU to GPU using the Slingshot environment. And here we are able to give very good performance on the bandwidth. And in the inter-node, here we are also the best, like a 4.28 microsecond. We are able to go from one of the AMD GPUs to the other AMD GPUs, and bandwidth is also very good. And here on the right-hand side, we are showing some of the collective number. Here also we compared with the RICL. As you can see, the RICL, in this case, we are able to do far better than even to the RICL. And here for the all reduce, I think more or less same, all the library except OpenMPI, they are performing very similar. So once again, the latest version is already working on this Slingshot 10. If you have any of these system, you should be able to directly utilize our stack. So these are some of the HPC very latest things in our MFS2 library. Now let me change the gear a little bit, and I'll move into the HDL and the other projects. So as I indicated earlier, like we're trying to provide a unified environment, like a convergent software stack. So for all these machine learning, deep learning application, many people use TensorFlow, PyTorch. Some of you might be knowing the Horobot, Torch Distributed, Deep Speed. These are the lower level frameworks. So what we have done a tight integration with our MFS2 library. So we have a project here, high performance deep learning. You can actually download our MPI library. We have a very detailed user guide. You can link Horobot. You don't need any other layer, any other software layer. You should be able to build on top of it. And that is our long-term goal, because most of the time when new networking technology comes, MPI libraries are the first ones to jump in and provide the support. So in that way, you cannot benefit multiple different domains instead of rewriting the software stack. So in this context, I'll try to show some results with data parallelism, out-of-code training, how we're handling hybrid parallelism. I'll try to show some use case like a digital pathology, and then also focusing on some machine learning QML applications. So here using our IDL stack, here I'm trying to show first some CPU-based number. A lot of people focus on the GPU-based training, but if you have access to a very large scale system, you can actually do even GPU-based training. So this is on the TAG Frontera. As you can see, using 2000 nodes, we can actually train ResNet 50 in 7 minutes. Okay, and we show you very good ideal trend there. And even for the GPUs, this has been running on the Livermore National Lab Lassen system. We are comparing here between our framework compared to the Nickel library a lot of people use. But if you do a very systematic evaluation, you'll see that using our MPI libraries based approach, you can actually enhance even 10,000 images per second faster using any of these frameworks. So those are with the data parallelism, but as you know, the model sizes are increasing in a larger and larger manner. So you cannot fit within one GPU or even the CPU. So here I'm just trying to show like an input message size and memory. So this is the range. You cannot do data parallelism. So we have been focusing heavily on the model parallelism recently. So here we have introduced a concept of HiPAR, hybrid parallelism. And here you can see some of the CPU-based number. This was presented at ISC 20. You can get a copy from the archive also. And this scales very nicely on like a 512 cascade lake system. We are able to deliver like a 481x speed up. And we get very good efficiency, like a 98%, 93% kind of things. So then after that, we have been continuously enhancing it. Here are some results on like a 1,000 V100 GPUs. As you can see, we are able to, this is the final solution, which is the green. We call it like a GEMS, GPU-enabled memory-aware model parallelism environment. As you can see, the higher is better. We are able to get on a 1,000 node, we are able to get like a 97% efficiency. But then the models are also becoming very complicated. And sometimes there is a concept of layers, multiple layers. So here we are trying to exploit subgraph parallelism. Okay, so given a graph like this, how exactly we try to allocate it to multiple GPUs so that we minimize the minimize the communication during the training. So this is we took the transformer model here. This paper was presented at the IPDPS last year. And if you see the results, this is again on up to 1,000 voltage GPUs. As you can see, compared to data parallelism, here we are able to like a two-way subgraph parallelism, four-way, eight-way. We are able to even boost the performance by a factor of 3. Now, finally, this is just a paper got accepted again for the ISC. So here we call like a 5-dimensional parallelism. So we call it Hi-Fi. So you have data parallelism, you have model parallelism, you have spatial parallelism, you have pipeline parallelism, and there is a bidirectional parallelism. So given any kind of a model, the question is how we can take the best combination of these 5 parallelism to boost the performance. And as you can see here, these results were run actually on 2,000 voltage GPUs. And as you can see, we were able to push performance by a factor of 2.67. Okay, so purely it's the same hardware. We are not changing anything, but exploiting the new kinds of parallelism, we are able to really boost the performance of the DL training. So that means if you are trying to do some DL training, we should be able to actually utilize it in a reduced time. So those are the kind of the actual models and the solutions. Now we are also working with some of the applications here. We are working with the pathology department here. As you know, like pathology images are quite large. So when we started working with them, in fact, they were just running it on one GPU. It was taking them 32 hours. Using 4 GPUs, we reduced to 7.25 hours. So gradually, we scaled it to 128 GPUs in just 0.46 hours. We were able to give like a 15x reduction in the time and 22x improvement in the throughput. So those are the kind of the deep learning. We are trying to take same MPI-based solutions for machine learning also. So here what we have done, we have introduced this like there is an MPI for Pi community. We have taken that and then integrated tightly with our MHAPIS2 GPU Direct RDMA library. Okay, so in that case, we made this release last year. We are actually working on a newer version. Might be in another month you will see a new release coming out. But if you take a look at here, these numbers are from the this ML HPC workshop paper. If you compare like the MPI driven with a nickel driven kind of things, these are like the k-means, nearest neighbor, truncated SPD. Those are like common ML benchmarks/application. We are able to give like almost 1.6, 1.4 X improvement compared to what you can get with the other solutions. The similar approach now we are taking to the big data things. As many of you know, we have also done a lot of work on the RDMA Spark, RDMA Hadoop, those kind of things. We are taking a little bit different route now, trying to link those with MPI-based runtime. Okay, so in fact, some of the things are coming up in the pipeline, might be in the next few months. I'll try to show like Spark running with MPI, Hadoop running with MPI. But here, what we have done, what I will try to show, the Dask. That is kind of a new data science environment a lot of people are trying to use. So what we have done currently, the Dask has support for TCP/IP and also has support for UCX. So we introduced this MPI for Dask. Okay, so we have gone through this route, MPI for Dask, integrated with MPI for Pi, and then integrated with our MFS2 GDR. So now the same library, whatever you would have installed the MFS2 library, you should be also now run Dask. You don't need any other libraries. And this again, the last year we have introduced this MPI for Dask release. Let me show some numbers. So this is here again. This is like a compared to IP over IB UCX. See the MPI for Dask. That's the red. The lower is better here. We are able to provide like a improvement 3.47, 6.92, and in this case also the other benchmarks almost factor of 2.9 and 2.9 kind of things. So that is kind of our convergence view, what we are trying to look for, so that in the end you just need the MPI library. So now you can actually mix and match. If you remember earlier I said on-the-fly compression. So if the MPI library has on the compression, you can actually utilize now for Dask also. Okay, you don't have to redesign compression in your Dask layer. So here, as you can see, same thing, just like earlier I showed for an HPC application like AWS, you can actually improve performance of your Dask data science applications. So you can improve the throughput by 1.56x. Execution time you can reduce almost by 37% by turning the on-the-fly compression knob. So these are some of the things what we have been doing on the on-premise, and as the things are being deployed, we are working with all the three major cloud providers, Azure, AWS, and Oracle. So these are like on the Azure, this is their ND A100 system, their GPU instances. You can hear so the MFS2 GDR is able to give very good performance, again, internode, intranode. Bandwidth here, we are able to go into 133 gigabits per second. And this is the SDR system. We are able to get the peak bandwidth. On the AWS, if some of you know, they don't use by the way, Azure uses InfiniBand. So all our software stacks can run there transparently with some optimizations. And gradually we are actually working with them to push the versions. But AWS is different. They use something called Elastic Fabric Adapter. Okay, they don't use InfiniBand. So we have actually done a special implementation for their EFA adapter. Many of the other MPI stacks go through libfabric. So we have a native design, and that native design actually, if you see here, WRF, as you can see, we are comparing our MFS2X with OpenMPI. As the system size increases, we are able to give far better performance, like 32% better performance, mini AMR, 21% better performance. We just had a paper accepted. This is in a workshop on IPDPS 22. We'll show more results. And this is, by the way, on their AMD, their ARM-based system. That is their system they are trying to promote. So these are all the numbers on the latest system. Same thing with the OCI. Oracle Cloud Infrastructure, they actually have gone through Rocky route. And since we support Rocky, we are able to actually get similar kind of performance benefits here, 2.7x, 21x better for some of the collectives. In fact, Oracle brought up the blog post. You can refer to that to get a lot of additional details. Now, while all these things are happening from the OSU side, there have been for the last few years, there have been a lot of traction from the commercial side. A lot of people actually want our solutions with real commercial support. So we have a commercial spin-off called Xscale Solutions. As I said, it's also a sponsor of this event. So through this, first we are able to provide commercial support, just like we can work with integrators, we can work with end users, HPC centers. So we are working with many of the worldwide national laboratories and supercomputing centers to really provide optimizations to these optimization of our libraries with a guaranteed kind of a service level agreement. we are able to provide these services. But in addition, we are trying to actually put value-added products. So whatever is available, I talked about MVAP2 DPU. The research is taking place from the OSU side, but the product is actually MVAP2 DPU is available there. We actually have another package from their side is called Xscale HPC. So this is on the purely HPC systems with a lot of optimization and fine tuning. For example, if you are trying to deploy a very large system, MPI library, any MPI library, as you know, has hundreds of runtime parameters. We can actually tune them before even users come on board. We should be able to tune them and make sure that all your applications get the best performance. We can also work with application people in terms of co-designing and for a given application, which parameters to choose or which parameters to change in the MPI library to boost the performance. So those kind of services are available from the Xscale solution side. On the machine learning, deep learning side, we have a product there called Xscale AI. This is based on MVAP2 GDR, but we have added 2 additional things. I'll talk briefly about this. One is called a deep introspect. Okay. So when you are running this application, how do you know that you are running, let's say, one application with your TensorFlow with an MPI library? Are you getting the really best performance? If not, what can you do? And the other one is a lot of these deep learning jobs run for a long time. You need checkpoint restart support, a scalable checkpoint restart support. So those are the 2 additional features which we have in this product. So here you can see it's like a dashboard. As your job is running lively, you can actually see how many all reduces are happening and how their performances are coming. So if you see here, like let's say here, it says this all reduce with this message size is very high. And then this is also latency is very high. So that means this underlying system is not optimized. The same thing. So visually looking at it, you can see where the weak spots are. And then in few hours, you can actually tune them. And then your performance gets boosted. And we have worked with some customers and we're able to give like a 25%, 30% benefit. So then with respect to checkpoint restart, of course, some of the, like the PyTorch, TensorFlow, they have some basic checkpoint restart. But as you can see, this is the green line. As your system size increases, like 128 GPUs, your checkpoint overhead continuously increases. Okay. So now the question is, can you do better? So here we have a solution. This is based on the Livermore SCR, Scalable Checkpoint Restart. So we have a version optimized on top of that called SCR Exa. So now you can see on the right-hand side, almost we keep constant, like around 10%, 15% overhead, we are able to take care of the DL training. So even your node fails, network fails, as long as some of the nodes are available under the SCR model, your deep learning training should be able to continue without any faults. So those are the kind of the things what I mentioned, like the value added things, which we are trying to do from the Xscale solution side. If any organization or if you are interested in those, we'll be very happy to talk to you from that side. So let me conclude. We are coming to the end of my time. So at a higher level, if you see upcoming exascale systems and cloud to be designed with a view of HPC, deep learning, machine learning, and data science. I presented some of the overview of the opportunities and challenges, presented a set of solutions. And as the technology is increasing, I mean, very soon we'll be trying to not just go through the exascale, but also zetascale systems. And this is where we are hoping that our converged software architecture will actually really help the end users with better and better benefits. So with this, let me thank all our sponsors. And these are all my heroes. These are all the past and current and past students, staffs who have worked a lot. Every time I give a talk, I salute all of them because these are all their contributions. So with this, I'll stop here and I'll be very happy to answer questions. Hussein, I saw you, you have turned on your video. So if you have any questions or anybody else, I'll be very happy to answer. Thank you.
Thank you, DK. Great session as always. I currently don't have any questions in the queue, so I'll just pass it to Hussein and see if he has any thoughts.
Thank you, Brian. Thanks, DK. Really, it's, as usual, impressive and very interesting talks. I mean, I really enjoyed the first talk, the keynote, a lot, and the last one, plus the rest of them, but these were just like very special talks for me. I have a question. You know, you define the cloud based on the available one. We're talking about Amazon, we're talking Azure, we're talking about Google. And these are typical, let's say, the difference is that they are running on, maybe some of them, they have virtualization, some of them like typical bare metal, and they're running over InfiniBand or whatever network. So I don't know if you had the chance to look at different approach where we define cloud, like orchestration, running on running MPI. I'll give an example here, like we have Kubernetes, and on pods, we are running now Slurm. So all the components of Slurm, they are running on pods. So we can SSH now to pods, and from there I can submit a batch, a strong running MPI jobs inside the pods that will be distributed across multiple pods. So
yeah, no, that is the new trend which is coming. We have not jumped into that yet, but we have some plan. We, like one of the students actually is looking at the Kubernetes and all. I know tomorrow Sadaf will be giving a keynote talk on that. I'm looking forward to that talk. If there is any kind of special optimizations are needed there, we'll be very happy to work with you and others on the community also.
Because typically we know that there are some overhead going there, and definitely, and plus in most of these systems are using Ethernet, so we'll not benefit from any no RDMA or other mechanisms. So but that's something that we are looking at and see at certain point how we can optimize that, because there are different approaches. We can give a customer the entire partition of a group and let them run on this cluster, or we can give them a namespace where they have all their Slurm environment, and from there they can submit whatever. So there are different ways to be able to maintain this multi-tenancy. But good that you are looking for this, because that could be interesting in the future. Definitely. Yeah.
Thank you. Yeah. Sure.
I think that's it, DK.
Okay, thank you.
Thank you again.
Thanks a lot. Hopefully we'll see some of you at ISC or some other place, or SC.
Absolutely.